So the 46th lecture, and I'll start with the article, the working and the circuit diagram of this center tap full wave rectifier. Now this center tap full wave rectifier, look at the construction of this or the circuit diagram of this. It consists of a center tap transformer here. This is center tap which is being grounded at the center here, and an AC signal of, say, suppose I say supply voltage Vs is applied to the primary of this transformer, and here you have two diodes. I name this as, suppose this is D1 and this diode as D2. Diode D1 and D2, assuming that these two diodes are identical, that is, they are having a forward resistance, both of them, RF. The forward resistance of diode D1 as well as D2 is RF. And suppose I assume that the load resistance here, this is the load resistance, and this load resistance I name this as RL is the load resistance. So this is the circuit of this, assuming very first thing is that this transformer is exactly center tapped and these two diodes are identical. Now this, whatever voltage I apply here, if the turns ratio of this transistor, of this transformer, is N1:N2, then based on this N1 on N2, this transformer can be either step up or step down. Of course, this voltage will be either step up or step down at these, between these 2 points A and B. Suppose I say this is point A and this is point B here, between point A and point B, and even suppose I say that this is point C here. Now, of course, this voltage, the voltage between A and B is halved, and suppose now I say that this voltage is VI. Input voltage, I assume this voltage as VI, or between this and this point, I say that this voltage is VI. The point to be noted here is that this VI is half of the step up or step down, or half of the voltage which is between these two ends of the secondary, and I assume that this voltage is VI here. And this, of course, it will be a sinusoidal waveform, so I am drawing either for this or for this. This is the input waveform VI, and suppose I say that the instantaneous value of this VI is Vm sine omega t. This is my input signal. Input signal means my input, I am considering the input between this ground and any one end of this secondary. This is Vi, not this, or even not between these 2 points, not between A and B. Vi is not between A and B. Vi is not equal to Vs. Vi is the voltage between, either you say between C and A or between B and C. So this is the input voltage. Very first thing to understand this. Now this is the input voltage. I say that this is 0. Suppose this point is omega t, 0. Then this is pi. This is 2 pi, 3 pi, 4 pi, and so on. Now look at the working of this. During the positive half cycle, I say that the during working, let's talk about the working of this. Working. What will happen that during positive half cycle, during positive half cycle of the input voltage Vi, during the positive half cycle of this, means I say during this cycle, when this is in the positive end, during the positive half, that is when I say that is when omega t, this omega t is between 0 and pi. When this is I am talking about this region during the positive half, means when this is positive, I assume that implies that when I say that A is positive, A is positive with respect to B. Suppose I say under this condition that, suppose I say that this is positive under this condition, I say that A is positive and B is negative. When this is positive and this is negative, of course this diode D1 is forward biased and D2 is reverse biased. I can say this implies that D1 is forward biased and D2 is reverse biased. I am writing as FB stands for forward bias and RB stands for reverse bias. So this D1 is forward bias and D2 is reverse bias. What will happen under this condition? Look at this. I'll draw the circuit here. Under this condition, it will be something like this, that you have this D1 is forward biased. This D1 is forward biased means this D1 here, this is A, this is point A. This D1 is forward biased, it will act as a closed switch. This will simply act as a closed switch. Of course, it is offering a forward resistance RF. No doubt, this is I am drawing the equivalent of this. This is point A. Then you have this load resistance RL. You have this load resistance RL here. RL. This load resistance RL is here, and this point is C, of course, is at the ground potential. This is point C, if you see here. And D2, D1 is forward biased. It will act as closed switch, and this D2 is reverse biased. This is your D1. I am treating this as, this is diode D1. This diode D1 is forward biased, acting as a closed switch, and this D2, as far as this D2 is concerned, look at this D2. This D2 is reverse biased, so it will, I'm sorry, it should not be open. It should not be, this line is not here. This is positive and this is negative. Of course, 0. Ground, this point is at ground. Assume this line is not there. Even this line, this actually this transformer is here, and this is open circuit. So if you see that the current will flow in this direction, the current will flow in this direction, and here no current flows through this when this is negative. Now if I say that the direction is this, it will, of course, this current is I. Of course, this current will be under this condition, form will be like this. This is D1 is on. I say this is D1 is on and this D2 is off. This D2, this is your diode D2. This is off, or this is reverse bias. This reverse bias means it is acting as a open switch. And again, when this becomes positive, let's talk about this during the positive half cycle. Either omega t between 0 to pi or between 2 pi to 3 pi, or next cycle when it is positive, it is something like this. The waveform is like this. Means under this condition, this is because of D1. This is the case when omega t is between 0 and pi, or during the positive half cycle, either between this is 0, this is pi, this is 2 pi, 3 pi, or between 2 pi and 3 pi, whenever this is positive. Let's take the second case. I'll take this is case 1. I'll say that this is case 1 here. Now oblique, I am writing here only with, I'll use some other color. Let's take case 2. Second case. Second case means during this negative half cycle. And of course the current flowing here. Can I say what is the value of this current under this condition? Under this current condition, the current will be I is equal to Im sine omega t. Of course, under which condition? When omega t is between 0 and pi. Now look at the second half. When during the negative half cycle of this input signal of this Vi, when the omega t, this omega t is between pi and 2 pi. So I'm writing here only, let me use some other color. I'm saying that during the negative half, I'm showing this negative half by this black pen. Negative half of Vi, when omega t is between pi and 2 pi, when I say that this omega t is between pi and 2 pi, between pi and 2 pi, under this condition, I say that during negative half means I am assuming this A is negative with respect to B. Means B is positive and A is negative. When I say positive or negative half cycle, that is I am referring this point. My reference point is this. When I say during the positive half cycle means A is positive with respect to B, and when I say during the negative half cycle means A is negative with respect to B. So I say when A is negative with respect to B. When A is negative with respect to B. Under this condition, what will happen? This is positive and this is ground. Of course, this D2 is forward biased, and you see that this anode is connected to negative, so D1 is reverse biased. So under this condition, I can say that this D1 is reverse biased and D2 is forward biased. I am writing in one line only both the statements. Case 1 and case 2. I am writing both the cases, one with green color, other with the black color. So it is very clear that this D2 is forward biased and D1 is reverse biased under this condition. Now look at what will the circuit under this condition. This D1 is reverse biased. D1 is reverse biased. It will act as open switch, and this D2 is forward biased. It will act as a closed switch, of course offering a forward resistance RF. So first of all, this D2, let me show it here. This is D2. This is D1. This D1 will be, since D1 is reverse biased, so it will act as a open switch. As far as D2 is concerned, I am showing this load here. This is the load resistance RL, this point. And this diode D2, if you see that this diode D2 is forward biased, so it will act as a closed switch. This is diode D2, but of course it is offering a current resistance RF. This is your load resistance RL here, and of course then I'm showing here this point as positive, and this is of course ground point here. Now what will happen under this condition? The current, if you see, the current will flow in this direction. The current I will flow in this direction. I will flow in this direction, and no current flows in this loop here. In this particular, since this is open. So if you see during the positive half cycle, the current flows. During the positive half cycle, the current flows in this direction. And during the negative half cycle, the current is flowing in this direction. The current is flowing in this direction, in the same direction. So I can show it here. Alright, let me show this by black pen only. Under this condition, during the negative half cycle, this is 0. Here, it is in the same direction. This is 0. Again, this is in the same direction. This is the case. This is the case when this, I am talking about this case. This is the case when omega t is between pi and 2 pi. This is the graph. This graph is for when omega t is between pi and 2 pi, whereas this green graph is for the case when omega t is between 0 and pi, when this diode is forward biased, this is reverse biased. In this case, this diode is reverse biased and this diode is forward biased. So I have shown these 2 points here. Now if you observe, the point to be observed here is that although here the polarity has been reversed, the input polarity is reversed, but the output which I obtain is in the same direction. Look at the direction here. Although the polarity is reversed across the load, the current direction is same. Here I am saying from my point of view, it is from right to left, from this side to this side. Although polarity is reversed here, but the current across the load is flowing in this direction only, whether during the positive half cycle or during the negative half cycle. And if I combine these two, if I simply combine these two, the output which I obtain here, of course this is 0, this is pi, 2 pi, 3 pi, again this is 0, pi, 2 pi, 3 pi, 4 pi, and so on. That is when omega, I combine these two, During the positive half, this is the case. During the negative half of this input, this is the case. I combine these two, and the waveform which I obtain is this. So this is the overall working of this center tap full wave rectifier. And of course, suppose I say that this is the output current I. Of course, I get this, the instantaneous value of this. The instantaneous value of this which I obtain at any point, it is equal to Im sine omega t. Im sine omega t. Overall, this is my final result for this complete wave. For this complete wave, it is this much, from 0 to pi. 0 to pi, this much. Pi to 2 pi, this much. I combine these two, this is, and if you see, now the full wave has been rectified. This was a case of half wave. If you see, it is a combination of two half waves. If I remove this, it is a half wave rectifier. If I remove this, it is a half wave rectifier. So the combination of these two half wave rectifier results in a center tap full wave rectifier, and the full wave has been rectified now. So it is called a full wave rectifier. Now look at the value of Im. I say that this I is equal to this I. Either talk about this I or this I. This I is equal to Im sine omega t, and this is Im. What is Im? That this amplitude, I am saying maximum value of this I is Im. Of course, Im will occur when V is equal to Vm. This Im will occur when V is equal, this is your Vm. This I will be equal to Im. Of course, when V is equal to 0, input voltage Vi is equal to 0, this is 0. Suppose this is 1 volt, it will be something value here. When 2, this will increase. When 3, this will increase. When this is at maximum, this will also be at maximum. So Im, now suppose I say that here this voltage is Vm, either at this point or this point. So I can say I is equal to, under this condition, this Im. When this V is equal to Vm, Im will be Vm upon Rf plus RL. Same thing as it happened in the previous case also. So here I can say this I is equal to Im sine omega t, where this Im is equal to Vm upon Rf plus RL. So these are the 2 points which we'll use again for the analysis of this, that I is equal to Im sine omega t for omega t between 0 to pi. It is not 0 for between pi to 2 pi, which happened in the case of half wave rectifier. So this is the overall circuit diagram working, and two elementary relationship between the current and voltage, or the maximum current and the voltage, and these resistances for a center tap full wave rectifier. The point to be remembered here, or the point to be noted here, that whatever I say Vm, which is the maximum value of this input voltage Vi, but this Vi is the voltage between the ground of a center tap transformer to any one end of this. So this is the main point that is to be remembered here. So this is overall about the working, circuit diagram and waveforms of this center tap full wave rectifier. I'll stop it here. Thanks for the time being.